Hello there, Mr. Wilson here again for what is another video in this Bridging the Gap series from GCSE Maths to A-Level Maths. So, as was in the first part, I'm going to talk through some key topics, well, one topic in this video that are familiar to you, or should be familiar to you from GCSE, but are fundamental for A-Level Maths. Now, in this episode, we're going to talk about Surds. Now, before we get into this, please make sure you're liking and subscribing because you don't want to miss out on any of these. And if you're getting ready for your A levels, you want to make sure you've got the whole selection of videos at your disposal. So in this video, we're going to talk about everything to do with Surds. Then I'm going to give you guys some questions to have a go at. So let's talk about some key things then. Well, first of all, what is a surd? Well, a surd is anything that is the square root of a number of which that answer is not a whole number. So, for example, things that could be surds, the square root of 2 is definitely a surd because this is approximately equal to 1.4, so on, but it's not a whole number. The square root of 5 is a surd, the square root of 11 is a surd, the square root of 99 is a surd. But things that are not surds, well, obviously whole numbers are not surds, so, just the whole number 5 is not a surd. The square root of 16 is not a surd because that is equal to 4, so that can't be a surd because it is a whole number. The square root of 2 times the square root of 2, and we'll learn about this in a second, that is not a surd because that is the square root of 4, which is 2. And you can have all sorts of other combinations. So anything the square root of any squared number, so a squared number being 1, 4, 9, 16, and so on, will end up being a whole number when you square root it. So they can't be surds. So it's obviously very important to understand, first of all, what is a surd? Because when we talk about rules in surds, we talk about simplifying. If we don't know what a surd is, then we're going to be pretty lost. So now that we know what a surd is, let's talk about the key sort of rule then. So the key rule of surds is that the square root of a times the square root of b is equal to the square root of a times b, which is quite nice. So for example, the square root of 2 times the square root of 5 is equal to the square root of 2 times 5, which is equal to the square root of 10. So you just times the numbers in the square root to get your answer. And this only works for multiplying. Right? This doesn't work for addition. We'll talk about that in a little bit. But that also means that you can sort of do it in reverse. So for example, if I was given the square root of 50, well, this could be equal to the square root of 5 times the square root of 10. Definitely. It could be the square root of 1 times the square root of 50, because again, those will multiply to make 50. It could be the square root of 25 times the square root of 2. Now, this one in particular is interesting. I mean, this one is interesting as well, but to a lesser extent. But this one here is interesting. And if you know why it's interesting, then you've discovered an idea about simplifying. The idea of this is that square root of 25 is the whole number 5. So this would be the same as saying the whole number 5 times the square root of 2, which we would write not like this. We would write it as 5 root 2. So what you have actually done is you've simplified the surd, right? Because the number in the square root has gone from 50 to 2. You've simplified it by splitting it into a squared number and a non-squared number. You've got to this sort of simplification. So let's have another go at a different number. So for example, if I gave you the square root of, 18. Well, the square root of 18 could be the square root of 1 times the square root of 18. It could be the square root of 2 times the square root of 9. And it could be the square root of 3 times the square root of 6. Now, some of these are not going to be very useful. Like, for example, the square root of 3 times the square root of 6 is not very useful to simplify because both of them are surds, right? And so you won't get one of them being a whole number. But this one, square root of 9 times square root of 2, well, the square root of 9 is 3, the whole number 3. So this will be 3 root 2. So square root of 18 is equal to 3 root 2. Now you might say, Mr. Wilson, the square root of 1 is 1, the whole number 1. That is absolutely true. It totally is. It is a squared number. However, this would then give you 1 times the square root of 18, which is just the square root of 18, and you actually haven't simplified it at all. It's the exact same as what it was originally. So we would basically ignore the square root of 1 times itself because we just get the same thing back. We haven't actually simplified it. So the simplified form of the square root of 18 is 3 root 2, which is quite nice. So you get these sort of wonderful little simplifications. So that's basically how we can simplify a surd. There actually might be, in some cases, multiple options. Okay, and I'll talk through one of those. So let me think of one off the top of my head that's going to work. The square root of 98. Okay, the square root of 98. Well, that is going to be... oh, actually, no, let me change that to square root of 90... I'm trying to think of one that's interesting, that'll have multiple answers. Yeah, the square root of 96. Square root of 96. Well, square root of 96 is the square root of 2 times the square root of 48. Well, neither of them are surds. It's the square root of 3 times the square root of 32. And neither of them are surds. It is the square root of 4 times the square root of 16. Is that right? No, it's 24, sorry. Not 16, 24. It's the square root of 6 times the square root of... This one's 16. It is 7, 8... Doesn't... Oh, no. Does 8 go into it? Yes, no, yes, no. 8 and 12. There you go. See, I got there eventually. So, see, that's what doing Maths Live does to you. Really makes you think. Now, there are actually a couple of options here. Right? You've got this one here, square root of 4 times square root of 24, because the square root of 4 is 2. But you also have this option here, because the square root of 16 is 4. Right? It's the whole number 4. So you might say, which one do you choose? Because this one will give you the answer 2 root 24. And this one will give you the answer 4 root 6, because the square root of 4 is 2, square root of 16 is 4. Well, actually, this is the most simplified answer, and there's a couple of ways to figure that out. One way, and this is the way I always think about it, is that you want the smallest number in the square root. So comparing these two together, the smallest number in the square root is 6, right, compared to the 24. So that has got to be the more simplified version. It's like if you have a fraction, even though you're making an equivalent fraction, even though all the fractions might be the same, the one that has the smallest numerator and denominator is the more simplified version, right? If you can't, divide it anymore, then it can't be, it must be in simplified form, which brings me on to the second point. The second way to tell is, if you can simplify the square root more, then it is not simplified. The square root of 24 can actually be simplified further into the square root of 4 times the square root of 6, which is 2 root 6. So actually the square root of 24 can be simplified more, which is why 4 root 6 is the most simplified term there. So that is simplifying surds, one of my sort of favourite ideas. Now this is the way I've always done it. There is an alternative way where you use the same idea as you would for prime factorisation to simplify it. This is a way that I have seen, and I have seen students use it, but it's not something that I personally like to go into. It's not something that I personally teach, but it is something that I have seen students use, and you are more than welcome to use it if it's something that you are comfortable with. So there's simplifying surds. Now, the tricky one is and by the way, just on a side note, if you're dividing surds, it works the same way as multiplication in the same way that, for example, the square root of 40 divided by the square root of 10 is equal to the square root of 4, because 40 divided by 10 is 4, square root of 4 is 2. So division actually has the same idea, where if you do the square root of a divided by the square root of b, it's the square root of a divided by b. So same idea. Adding and subtracting surds, that's where it gets tricky, right? Because you are only allowed to add surds if they are the same square root, which is weird. It almost works in the same way as algebra, right? So for example, 2a plus 3a plus 4b, well, that would be 5a plus 4b, right? You wouldn't add the a's and the b's together because they are unlike terms. They're not the same letter. So you wouldn't add those together. It wouldn't be 9ab because a's and b's have to stay separate when you add them. For the same idea that if it was 2 root 2 plus 3 root 2 plus 4 root 3, well, this would equal 5 root 2 plus 4 root 3. You wouldn't add these surds together to make root 5 because they are different surds. So it is the exact same idea. So if you can simplify in algebra, simplify like terms, then you can do adding in surds. It's the exact same idea. If you can simplify like terms, adding surds is the exact same idea. So, obviously we need to be aware of this, that you can't just add these surds together. It's so tempting for students to say that this 2 plus 2 plus 3 is 7, so it must be root 7. It's so tempting, but you can't do that. That's not how surds work. Yeah, you multiply them if it's multiplication, you divide them if it's division, but in adding and subtraction, it is not the same idea. So then you might say to yourself, okay then, well, what happens if I have different surds? Then I can't add them. So for example, if you have the square root of 32 plus the square root of 8, well, on first glance, you can't add these together because they're not the same square root, and you can't say it's the square root of 40. But in actual fact, you can add these. You just have to change them. Using the skills that we know above about simplifying, you can actually simplify these in order to add them. So for example, square root of 32 is the square root of 16 times the square root of 2. Now I know this is the right one. Obviously you could list them all out. So you could do the square root of 1 times square root of 32, square root of 2 times square root of 16, square root of 4 times square root of 8. You could list them all out, absolutely. But through experience, you kind of just get a very quick sort of knowledge on which one's the right one. So the square root of 16 times square root of 2, this could be 4 root 2. And the square root of 8, well, it's the square root of 4 times the square root of 2. So this is 2 root 2. Well, would you look at that, right? The number under the square root is exactly the same. So now we can add these together. So this would be almost the same as saying 4a plus 2a, sorry, and that would be 6a. Well, this is going to be 6 root 2. You do not add the numbers in the square root, right? Similar idea to, like, you wouldn't say that 4a plus 2a is 6a squared. That's not really how it works. So for the same reason you wouldn't do that, 4 root 2 plus 2 root 2 is 6 root 2. So that's where that answer comes from. So you could be, and a very key idea, be asked to sort of use your knowledge of simplifying surds along with adding surds to make them the same so that you can actually add them. The final key idea then about surds, and one that is very essential for A-level and getting you ready for that, is rationalising the denominator, a higher tier skill at GCSE. What I mean by this is, let's say you have a fraction which is 4 over root 2. Well, the square root of 2 is irrational. All surds are irrational. Basically, that means that they can't be expressed as a fraction. The square root of 2 cannot be a fraction. It's an infinite decimal like pi and e, which you'll meet at A-level. They're all irrational. So what we mean by rationalise the denominator is that the denominator of this fraction, we don't want it to be an irrational number, we want it to be a rational number. Now you might say, at GCSE, you might have sort of just gone along with it. But a good mathematician should be thinking, why are mathematicians so obsessed with rationalising the denominator? What difference does it make? Because when you actually rationalise the denominator, the surd ends up being on the top, on the numerator. So what difference does it make whether it's on the numerator or the denominator? Well, think of it like this, right? If you were asked to do some kind of division, right? If you were given two fractions, so for example, 4 root 2 on this side, and I'm just going to make up root 3 over 2. This one is much, much easier to work out without a calculator, right? Because in A-level maths, you can actually approximate the square root of 3. There's an approximation value for it, and then you just have to half it. You divide it by 2, you just half the value. And yeah, it'd probably be some approximation because it's an infinite decimal, but it would be so much easier than trying to do 4 divided by the square root of 2, and the square root of 2 is about 1.41, so on, right? So, or 1.42. So you would have to divide by an infinite decimal, which is way trickier than divided by taking an infinite decimal and divided by a whole number. So it is, and you'll realise this at a sort of higher level. It's significantly easier at the higher level to divide by a whole number than it is to divide by an infinite decimal, and that so you'll sort of use that kind of skills in your A level. So rationalising the denominator is a key skill and is so much more useful than maybe what it's made out to be at GCSE. It's just at GCSE it's one of those things that they sort of ask you to do, and it's not really something that you are necessarily thinking, why are we actually rationalising the denominator? Why do we want to do that? A level gives it a bit of a purpose. Anyway, how to rationalise the denominator? Well, if the denominator is just a square root, it's just a surd, then you multiply the numerator and the denominator by that surd, the same surd. The reason for doing this is because when you multiply a surd by itself, you get a whole number, guaranteed, because you are basically squaring the square root, right? So the square root of 2 times the square root of 2 is the square root of 4. But the square root of 4 is 2. And then the square root of 4 times root 2 is 4 root 2, so this would be 4 root 2. And you're left with this, so 4 root 2 divided by 2, well, that's just going to be 2 root 2, because 4 divided by 2 is 2. And we don't do the square root of 2, we don't divide the number in the square root, we just leave that. So we end up with that. So that's a nice little idea. There is a trickier version, which is definitely at the top end of GCSE, which is where you have something like this. And you have to rationalise the denominator. Now, in this case, to rationalise the denominator, you have to multiply the numerator and the denominator by the opposite sign in front of the square root to the original. So in this case, because it's 1 minus root 2, we're going to multiply the numerator and the denominator by 1 plus root 2. And I'll explain why we do this, because, like I said, at GCSE you're sort of told that that is the case, but maybe not understand why do you actually do that. And I think, especially at A-level, it is key to have a deeper understanding of mathematics, right? There has to be a purpose for why you do something. It's not just made up, you know what I mean? There's a reason why that rule exists. It's either proved in mathematics, or it's useful to do it that way, or it links to something else in mathematics, which allows you to do that thing. So there has to be a reason why the opposite sign in front of the square root, multiplied by that, will give you a whole number as the denominator. We'll talk about that now. So the numerator, by the way, 3, you just times the 3 by each term. So 3 times 1 is 3, 3 times root 2 is 3 root 2. Now, the denominator, you need to do 1 minus root 2 times 1 plus root 2. So I'm going to put them in double brackets. And you basically expand these as if you were expanding normal double brackets, right? So you might want to use, I use a grid when I expand. So I put 1 minus root 2, 1 plus root 2. 1 times 1 is 1. 1 times negative root 2 is negative root 2. 1 times positive root 2 is positive root 2. And positive root 2 times negative root 2 is negative root 4, but root 4 is 2. So it's going to be negative 2. And you might notice something interesting happens. You know you're doing it right because you should end up with a whole number. That's the whole point of doing this. In actual fact, these square roots are going to cancel. right? Because plus root 2 and take away root 2, that's just 0. So what you're left with is 1 take away 2, which is minus 1. And technically, if you divide it by minus 1, everything turns negative, so this would be the correct simplified final answer. Now, again, I'm going to link back to that why. Why does this work? Why does choosing the opposite sign give you a whole number in this technique for rationalising the denominator? Well, it actually links to another technique of expanding double brackets in normal maths, which is if I gave you this and asked you to expand it, you would get x squared plus 4x minus 16, which would be x squared minus 16. This is a special type of quadratic, right? It is, as my students will never never get tired of hearing me say it. This is dots, right? The difference of two squares. It's a squared number, take away another squared number, and what you are left with, well, when you factorise it, you get this opposite sign because there is no x term here because the plus 4x and the minus 4x cancel each other out. So what you've actually done in the rationalise the denominator question is you've almost done the difference of two squares to cancel out the surd, to cancel out the x term in this case, but to cancel out the surd here. It is the exact same technique mathematically. You've just replaced, in this case, you just replace this number with this surd and x with this number. That's all you've done, but it's the exact same idea. So if you understand expanding double brackets, then really that sort of idea should link to this in the, oh yeah, it actually does make sense why we choose the opposite sign and we do it that way in order to cancel that term. So I love dots. It's one of my favourite techniques in mathematics, and to see it sort of play out here is really interesting. Now, one of the very last ideas then is about actually expanding brackets, which links to this rationalise the denominator. So just like with sort of single double brackets in algebra, you can expand single double brackets with surds. So for example, the square root of 3 brackets 4 minus the square root of 2. Well, just like you would normally do when expanding brackets, you multiply every term on the outside with every term on the inside. So root 3 times 4 is 4 root 3. And traditionally we put the number before the surd, that's traditional, and then root 3 times root 2 is root 6, so we get that. So that is that expanded. And then if we were doing double brackets, just like I've already shown you, you can use whatever technique you want. They don't have to be opposite signs, they could be completely different. I'm just picking random numbers. But you want to multiply, some people like to do sort of this claw method, or the foil method it's sometimes referred to, or the grid method, whatever method works for you. But you just need to multiply every term from one bracket with every term the other, vice versa. 3 times 4 is 12. Oops, that is the weirdest 12 ever. 3 times 4 is 12. 3 times root 3 is 3 root 3, negative. 4 times root 2 is 4 root 2, and root 2 times root 3 is root 6, but it's a negative because it's positive times a negative. Just be careful. If you are obviously multiplying two negatives together, it's going to be a positive. If you're multiplying a positive and negative, it's going to be a negative. And you're left with this, and we can't simplify this because we can't simplify the square root of 6, or the square root of 2, or the square root of 3, and so we can't add them together because they're not the same square root. And even though this sort of answer looks a bit untidy, it looks a bit messy, it is genuinely the correct answer, and we should just sort of just go with it. So that is basically a whistle-stop tour of the surds. Now it's a chance for you guys to give it a bit of a go, and for me to take a bit of a sip of drink and let you guys have a go at some questions. So these questions I just found online from Maths Genie. They're fantastic questions. I'm not obviously going to go through all of them. That would be ridiculous. But I would highly recommend going to Maths Genie and checking out these questions because there are some absolutely fantastic questions here. So what I'm going to do is I'm going to let you pause the video here. Have a go at these first. We'll just say the first two questions. Let me scroll. The first two questions here. I'll go through them. Give you some more questions. I'll go through them and so on. So pause the video now, and have a go at these questions. So hopefully you've had some time to have a look at these questions. Let's give them a good go. So the first one. The square root of 48 can be written in the form k root 3, where k is an integer. This is basically just the simplifying stuff that we looked at right at the start of this video. So the square root of 48 is equal to the square root of 16 times the square root of 3. Well, the square root of 16 is 4, so this would be 4 root 3. So k is 4 in this case. And then for the second one, same idea. The square root of 25 times the square root of 2 is the square root of 50. The square root of 25 is 5, so this would just be 5 root 2 for the second one. So a nice little simplifying question there. Very key idea when going on to A-level maths. Now, have a look at these two now, these rationalise the denominator questions. Again, pause the video now to give them a good go, then I'll go through the answers in a second. So pause the video now, give these two a good go. Rationalise the denominator. If you need to look back earlier in the video to how I did this, then please feel free to do so. So hopefully you've had time to look at these. We need to multiply the denominator by the square root of 3. So 6 times the square root of 3 and root 3 times the square root of 3. So we get 6 root 3 over 3, because the square root of 3 times the square root of 3 is the square root of 9, so that would be 3. And this simplifies. 6 divided by 3 is 2, so this simplifies into 2 root 3. You can actually do the same idea with this, right? So the rationalised denominator here, well, we've got, you multiply the numerator and the denominator by the square root of x, so you get x root x all over x. X divided by x is 1, so this is just equal to the square root of x, which is super weird. But that's what it ends up being, right? It would almost be like saying 2 over root 2. You times the top and bottom by root 2. You get 2 root 2 over 2, which is just root 2, so it's just be root x in this case. So a nice little interesting second part there. Now, I'm not going to go through every single question here, although there are some absolutely fantastic questions like this question 17, for example. A really interesting question where you have to rationalise the denominator twice over using two different techniques. And this one with surds, with letters, is also really interesting. But I would just, because obviously I don't want to take away from Math Genius for getting these questions, so I would definitely recommend searching up these questions and giving them a good go, because the thing about maths is the more you practice, the way better you get at it through practice. It's just, it can be really difficult sometimes where it's just not settling in whatsoever and it's not really working out for you, but through practice maths tends to get a lot easier. So I'm going to leave it there for this video. There are lots and lots more videos that I've got in my mind, such as